message to all of you that this webinar will be recorded. Also for the people that cannot join or join too late or whatever, it can be played back. Just to go through the agenda, a little bit of my background. I'm chairing the electronic HTSML electronic steerco. But this whole setup of these webinars is done in close cooperation with Holland High-Tech and High-Tech NL. So it's already the fourth in a series of seminars we had. So you see them listed here. We had Yole Development giving a broad view on what is cooking in the landscape, the global landscape, with different applications of microwave radar technology. Then we have Frank van Vliet from TNO talking about radar in defense and security. Then we had Cicero, one of my peers in NXP, talking about NXP and radar systems in automotive. And then today will be dedicated to RF and medical applications, where Klaus Werner from Pink RF will give the presentation. I will introduce him in a second. Just a little bit for bookkeeping things. The presentation will be recorded. If you do want to be visible during the Q&A, please switch off if you do not want to be visible, switch off your video, and the link for the recorded session will be distributed later. Then a little bit about MS Teams. If at the end we have a Q&A, you can raise your hand with the hand button. If you want to see who is in the meeting, that's also fine. You see the sign here, and you can post questions in the chat box. Yeah. So then the agenda, well, a few opening remarks. I will flash a few slides. Then in about 8 minutes, Klaus will take over and we'll talk about RF in different medical applications. And we try to get enough time for some Q&As. If the time is up at the end, then Q&As can always be there in follow-up interaction, I would say. So yeah, electronics, the roadmap scope. So what are we trying to achieve in the Netherlands? Well, to start with a few sentences here, electronics is pervasive in all aspects of society and daily life. The roadmap joins universities, international corporations, SMEs, and institutes around an innovation program that spreads from chip technology to component to integrated circuits to electronic systems. So yeah, actually electronics are quite enabling for many high-tech systems material roadmaps and supports all societal teams and the key sleutel technologies. You see it also here in a little bit more graphical view. More than more, maybe a lot of you are familiar with more and more. More is doubling the chip density every half a year or every year, but there is more than more. It's also not only the scaling of the semiconductor industry, but it's also the scaling along the axis of analog, passives, high voltage, sensors, actuators, biochips, all coming together. And combining these things will lead to higher value systems. But the enabling factor here is electronics. So what more and more electronics bring is more miniaturization via chip technology, via packaging, but also flexible electronics. And we are busy with setting up a series of seminars for printed electronics. And we will get more information to all of you in the coming weeks. Then more and more electronics also bring zero power for energy scavenging, for battery technology conversion efficiency. We also bring user-friendly devices on and in your body, and that's where we talk today about even in this domain, healthcare, and medical domain. But also it brings devices you talk to, like Siri, Google. Can you imagine that you could live without Google? What do you do what to do and how to interpret all massively generated data. Then it also brings sensors, actuators, and interfaces together, electronic noses. Even the smartest watches nowadays, they even measure not only blood pressure and heartbeat, but also your other things in your body already. So then there's this whole battle about bandwidth. We talk about in NXP now, we are busy with 6G, but also Wi-Fi 7 or Wi-Fi 8, but also USB X, USB 4 or 5 to come. So it's all about the battle of bandwidth, higher data rates, etc. And then we have the network connectivity, communication, automotive, and standards, define, connect, and inference. Without electronics, this all would not be possible. Without innovation in electronics. So the takeaway here, and then I hand over to Klaus and introduce him first. The takeaway is electronics R&D roadmap is enabling for many high-tech systems and material roadmaps, and supports all these societal teams and the key sleutel technology. So my message would be, you have to keep innovating, keep inventing, keep investing, protect the NL created intellectual property, and keep an industrial footprint in NL. There's never coming an end to more than more, although some people believe that there is an end to scaling of chip technology. Well, that's a discussion I hear already for 30 years. So that will never come to an end, most probably, and certainly more and more will bring even more. So collectively invest in electronics, collectively look in the seminars. We took care of the last 3 seminars, but also today's seminar, what microwaves can bring us more. So now, yeah, I hand over to Klaus, but introducing shortly. So welcome, Klaus, and welcome, and thank you for volunteering to give a presentation to the setting of these webinars. You co-founded Pink RF in 2015 to develop and sell RF energy systems. And within Pink RF, you developed, still developing, innovative systems that apply the energy of electromagnetic fields generated by semiconductor-based RF and microwave generators to heating matter in the broadest sense of the word, ranging from single kernels of corn to pop dose up to 1,000 liters of soup per hour, from cooking, overheating bodily fluids to medical diagnostics. And the applications of the technology are very widespread, and we know that that's already addressed in the first seminar from Jo, that this RF has a very broad span of different applications and domains. You authored a number of papers and book chapters in the field, and you are chairing the solid state RF energy section at the IMPI, International Microwave Power Institute. And you graduated, going back some time, I would say, from Aachen University as a physicist, and you hold a PhD in the semiconductor technology from Delft University. And you worked at Philips Semiconductor, and you were a peer in NXP, for me even, in various managerial and business development roles prior to your new adventure. You started being consultancy and starting this Pink RF initiative company. So with that, I would like to thank you again for being today's in the 4th webinar and giving a presentation. I will stop sharing and then you take over. Success, yeah?
Yeah, thank you very much, Hans, for the very kind introduction. And thanks for the organizers for giving me a chance to talk about things that I really like and that I developed passion over the years for. So it should not be too difficult. My concern is only that I be able to take the audience along, but please interrupt and or raise your hand. I don't know whether, Hans, you're going to take a look at the raise your hand kind of stuff.
Yeah, we will take care.
Okay, cool. So then interrupt me, please, because I don't see that now anymore very well. I hope you can see my screen.
We can see your screen, yeah.
Very well. And then I'm going to go into the laser pointer mode as well. Right. So I was asked to talk about RF and microwave energy for medical applications. What we will hear about is a bit about the RF energy by itself and how we look at it from a Pink RF side of view, And then I will give a number of examples of RF use in the medical applications. And I have to apologize right away because I'm very sloppy in the use of RF or microwaves. When I'm talking about RF, I also include microwave-based applications, and we'll see where that comes down to in a second. And I'll draw some obvious conclusions in the end. The grand idea of RF energy will be the first part, and this is not to overwhelm you, but to give you some perspective. This is the electromagnetic spectrum. Part of it we all know very, very well, which is our light environment. Light is basically also an electromagnetic wave, and again, I need to apologize for all the folks who this is obviously very, very clear to, but just to make sure that everybody could and can follow, I like to dwell on this a little bit. So here's our light, ranging from the red to the blue in terms of increasing energy. And I'm showing this again to give you some perspective. On the left-hand side, we will find, say, all the radio spectrum and the broadcast, wireless, and the microwave stuff. So here is where we talk about RF and microwaves up to about 10, 30 gigahertz. 3 gigahertz, actually, to be correct, is usually the microwave field. Then we're going to the millimeter fields, and then you have terahertz stuff. And you also see along some basic applications that come back here, like currents that are being induced on magnetic side, heating. And here we have obviously all the light. And the thing starts here to become really dangerous when we have very high energies at very high frequencies. We have enough power per quantum to actually ionize chemical bonds and to break chemical bonds. So this is the place where also here, starting in the ultraviolet side of things, the sun can create cancer in our skins and or actually look through everything and create cancer, ionize, and can be detrimental to humans for sure. Just to go a bit back on the RF side, here you see also a couple of the major applications. Typically, we think about RF in terms of data communications, or microwaves in terms of communications, and you've seen that also in the previous presentations. And amongst others, we all know our microwave oven that runs at 2.4 to 2.5 gigahertz in a so-called ISM band, industrial, scientific, and medical band, where you can freely emit the energy unless you are crossing some boundaries. So one more thing to stress, we are talking here on the lower end side about non-ionizing radiation. So fundamentally, this radiation is not able to break any bond in your body, but it will be able to heat things and heat matter during the exposure of the matter to the radiation if things work out. And I'll be back on that. Definitely, we're staying far away from the ionizing part of the energy. So usually all our radiation that we create is intrinsically safe. Now, one more time. Usually when we talk about RF and microwaves, we think in terms of data communication. We think in terms of transmission of videos or communication via our cell phones. And that is all done using semiconductors here on the left-hand side. We have a synthesizer that creates the high frequency that we need. And we have a PA, power amplifier, that creates necessary power level to then transmit through an antenna into space and being received by some receiver, which could be a cell phone or the television set or something like that. Now, within our use, within Pink RF's use of the electromagnetic fields here, we try to put the energy in those fields to good use. And that we use the same kind of technology that is available also from the cellular base stations, for example, and synthesizers, amplifiers, and we don't radiate the energy into free space, but we radiate it into an applicator, as we call it, which is the volume in which the process takes place of having the RF or microwave hitting the object that should be heated, and confines the radiation also to that kind of volume. So we definitely don't want to radiate all our power into free space or to somebody standing next to it, because that can be dangerous given the fact that we are radiating, or that we're producing power levels up to 10 kilowatts here at this sort of antenna point. So you need to confine the radiation for a number of reasons, and I'll be back on that. Also for the application, not in last place. The beautiful thing is that the semiconductors allow you a very, very high degree of control and also feedback. So you know how much power you put into the system and how much you get back. And I have another slide on that. The source that we're using is a solid state standing for semiconductors, basically based generator, which is a number of transistors that run at very high frequency and very high power levels in a chain to generate the output power level that you need for your application. And like Hans also mentioned a second ago, I would think that the high power, high frequency RF or microwave generation is definitely part of more and more for a lot of reasons. And Philips here in particular in Nijmegen, and I'm happy to sit here in building A, which is the first building that Philips Semiconductors at 1953 put down to actually manufacture germanium at that time, solid state based transistors that quickly moved into silicon, and also looked into the fact that the site here in Nijmegen grew a lot up to the ICN8 factory here, which is one of the nicest 200 millimeter fabs in Europe. And they also run processes that are geared at maximizing the power and the frequency that you can push out of silicon. So that's clearly more definitely also happening here in Nijmegen as we speak. Back to my story. So we create an electromagnetic signal, which is basically, as we call it, one RF vector at a time. So that vector has the properties of having some frequency, having an amplitude, and together with other similar frequencies can have a phase delta with respect to the other signals in the system. The beauty is that it is a very clean spectral source, meaning that you have just the frequency that you're interested in. You don't have a band. This is actually Wi-Fi in the lab when I took that measurement, and it also allows you reproducibility. That seems to be relatively trivial, and in being used to semiconductor-based RF, that is also the case. But I usually need to defend myself and/or advertise our technology here against magnetrons, which is an old tube-based technology that I'm not going to go into, but that we all know from our microwave oven currently at home. It's that cheap, and you can create a lot of power with it, but it is basically completely uncontrolled. And in here, we want to make sure that we have full control over our signal, because we need to have that in order to make sure that the amount of energy that we deposit in the processes is very well known. If you imagine sensitive processes like, for instance, heating up humans, which I will be back on as well, in hypothermia or therapy treatments, then you need to make sure that you know exactly how much power you are offering towards the patient. Otherwise, you don't want to burn it. You want to have the right amount of power. So that is what this technology also offers you. You know exactly how much power you're putting into the system and into your process. you have, in that sense, calorimetric process control and also the quality associated with that. If you think about soup, for example, that you need to pasteurize, you don't need to overheat it. It also offers some kind of network analyzer functionality that is something that has to do with the fact that the amplifier, the generator, can measure the power that it delivers into the system, but it can also measure the power that is being reflected out of the system. That has to do with the wave character of electromagnetic radiation. And you know that from a lot of mechanical waves that you experience every day, or even from light, that it reflects back from surfaces that are somewhat reflective. And that, in our case here, we call that, in RF case, this is called a matching problem. If the system is not very well matched to the generator and the impedance levels of the generator output, then power is being reflected out. And this impedance that the system offers is a strong function of the process inside. And again, we will see that in a number of examples coming back. But making use of that network analyzer functionality that you have there, you can sort of talk to your load. And there's a famous oven from Miele, so one of the few consumer-based ovens that cook food that are also called like that. It's called a dialogue oven, because they want to stress the notion that they can sort of talk to the load by analyzing what's going on in the oven while they're cooking. For other purposes, the agility plays a big role. I don't think that much for the medical applications, but just to mention it, for industry, it's important that at high power levels, the arcing is suppressed and that you can react quickly to it. And you have chances to protect your electronics and processes if you're fast enough analyzing what's going on. One slide on the interaction of the radio frequency. So it is electromagnetic radiation, as we said, non-ionizing. We have relatively low energy content per photon. And the beauty is it's non-contact, so we can have the radiation created at some place and then acting some other place, like through an antenna in free space. It is selective. That means that you have different materials reacting differently to that radiation. As we all know, for instance, like a metal surface would not absorb our RF or microwave signal, but it would rather reflect it. That's why we're working a microwave oven, and it doesn't absorb with its walls. It's a cold wall system, but it would reflect the power back that is not directly used by the food. So the metal is selective. We're not heating that. It is very clean, so there's no other medium involved that needs to transfer the energy, and it can be very efficient. We have a high, say, generation efficiency, and we can also have a very high efficiency of putting the power into the system. So if you look at the overall efficiency, that has to do with, of course, creating the RF from DC sources or some mains power, and then you put your power into the system, you can have very high efficiencies of making sure that the power that you created really ends up in the system as well. And that's not a trivial thing. There's this one, there's a couple of phenomena taking place to actually absorb the energy, and that for the most dielectrics, like materials that are isolating, that happens via dielectric heating. You need to imagine that some dipoles are wobbling in there, and during the wobbling, they sort of drag with respect to the environment and create a bit of friction. It's absolutely not like that, but just to give you an image on how you could think about it. So it heats up, and there's also ions, like in the salty liquids, you have NaCl dissolved, and the sodium and the chlorine atoms are moving in in the field are being pushed by the field back and throw, and that also creates some resistance, or in the overall resistance, it just dissipates power from the field into the liquid or paste or whatever you have there, because it does not need to be a liquid at all. It can be solid state up to whatever. This formula, just to indicate what plays a role when you look at the power that you can put into particular materials. This is all constants. This is the frequency. So the higher the frequency, the more likely you are to absorb. This is a material constant. It's part of the permittivity. So next to the dielectric constant, we have the so-called loss factor that describes the properties of materials with respect to RF or microwaves. And this is the loss factor, and the higher the loss factor, the more power you obviously per unit volume you can absorb in the material. The loss factor is a function of the frequency, and then you have the amplitude of the electric field squared. It's the average field squared that gives you the power that you can consume. So based on the material that you look at and this particular factor, you can get an idea also on how deep RF, for instance, penetrates into material. The higher this factor is, you can imagine, the more is being absorbed and the less energy sort of goes through because of the fact that everything can get absorbed very quickly. So when we design processes, we look at that formula, we look at the numbers, and we look at the volume of the material that we need to heat up, and then sort of choose the frequency and or say the volume that we're working in, such that we can achieve the required homogeneities and energy per unit time absorption. The other thing is, and that may not be so directly clear, is that reflection, diffraction, absorption, and things like that are exactly like in the optics that you also learned at school. So there's things like total refraction, there's diffraction phenomena taking place, and it's in the end, it's obviously quantum mechanics, but I put this here because, for instance, for the MRI system, the magnetic resonance imaging system, it's really deep quantum mechanics that allow you to create images with that kind of radiation. One other ingredient is, as I mentioned before, is the type of applicator. They have, next to the point that they need to confine the radiation that you create, they need to make sure that the radiation ends up where you need it. If you and there's a couple of basic geometries that you can have, and depending on the frequency that you want to radiate into that kind of geometry, you get particular possible field distributions inside. So for instance, in this cylindrical form, here we have radiated some electromagnetic radiation. Doesn't really matter what kind of frequency it is now, but there is a condition based on the geometry and the frequency and the wavelength of that wave, that this kind of electromagnetic standing field develops, or that, in other words, the energy distribution that you can achieve in the cylindrical example is such that you have a very high electrical power density in the center, in the central axis of this applicator. So if you wanted to, for instance, heat a liquid, you could, for instance, consider this kind of applicator. You run the liquid through in that sense. You make sure that you can pump RF or microwave energy into it in a way, and then you would be able to determine that the liquid is heated in the center in first place. Another example here is one that uses a so-called mode, which is basically the double type of the mode of this applicator. You have two hotspots, two centers or locations of a lot of energy density. So if you were running, just making this up now as I speak, liquids outside of these hotspots, you would not be able to heat anything. You need to make sure that your material that you want to heat is located here, and you can turn it around, of course, and make sure that by putting the material right there, you know exactly how much energy you can put into those locations and into the material that you have there. There's another type of applicator. These are the applicators that are sort of free space type of applicators. You radiate the fields into it. This is an applicator that makes use more like of a resonant circuit. Here we really have just an LC type of resonator with a coil and some capacitors, and using the right frequency, we're able to capacitively couple power into, say, for instance, liquid that flows through this applicator and heat the liquid up at a suitable frequency. So that this is not free space, this is more using a capacitor type of approach that has a lossy dielectric, and we put our material to heat through that capacitor as the lossy dielectric. Just to give you an example how these applicators could look like, and we'll see examples in a minute. This is one example that we all know. This is our microwave oven at home, and in this case it's a cavity that we simulated with 2 antenna ports and generators that are running on the same frequency between 2,400 and 2,500 megahertz. And what you see is, depending on the frequency, there is different patterns of the energy distribution that develop inside. And that would also mean that when you put food in there, there is frequencies that do not heat particular positions of your food. So I swear that you would look at your microwave oven at home differently tonight when you go back home. Because this is exactly what happens in your microwave oven at home. Although only thing is that the system is not driven by solid state generators, but by a magnetron, which is basically all over the field. So what the people try to do all over the place in terms of frequency. So what the people try to do is offering a large bandwidth of frequencies that they sort of hit all the possible modes that can develop in the microwave oven, and that present a particular energy distribution in the oven so that the pizza gets heated everywhere. And to improve that, even they use the turntable, so that's why we run around with the pizza in the microwave oven. But I can tell you that it doesn't work to the full extent of what the idea is behind it. And we all experience that regularly with trying to reheat pizza in a reasonable way. And I can talk a couple of hours just about heating food, but I'm not going to do that because the idea was that we should look at RF in the medical field. But again, you can use the RF for lighting purposes, for cooking, as I mentioned. There's a lot of plasma applications, amongst which is cutter. There is plasma ignition, so for a better type of spark plugs. And there's a couple of applications that I will come back on with respect to using RF in the medical field. Well, I was actually quite surprised when I started to work on this presentation because I'm not everywhere in the medical field. There's obviously existing applications. I was quite surprised to find that many in the end that already make use of the RF. And just to categorize them a little bit, there is, for instance, sensing and imaging as applications, which makes use of RF. There's definitely heating. And there's also a lot of applications that are based on the creation of plasma. And I'll be back on a few of them, not all of them. And for instance, here, that is one thing I came across that I knew about of sorts is a thawing application. And this guy here, this so-called Genesis plasma therm, is actually thawing plasma and blood bags that are frozen without water bath, so no contamination, and within reasonable time and faster than the water can do it, so that the patients that need the plasma badly can be helped quicker. And that is already also making use of RF energy rather than the, I believe, standard, which is the water bath, but has definite disadvantages. So again, we have imaging here like magnetic resonance imaging. We have electron spin resonance imaging. I will not be back on that one. For the heating, we will see ablation. There is electrosurgery in general, which also I'm not going to dwell on. There is aesthetic treatments that you can do by heating up locally. There is hypothermia thermotherapy that I'm going to dwell on. There is liquid heating. I have a couple of examples about that. And for the plasma part, there is systems on the market that look at skin rejuvenation, look at sterilization of, for instance, how to say, the knives, the scalpels of the surgeon, and whatever you have in the operating theaters that needs to be cleaned. That is partly done with a plasma environment. And then there is cleaning. For instance, the company here in the neighborhood, which is called Plasma Cure, they produce a particular plasma applicator to clean long-standing wounds in a very effective and smart way. Now, a bit about MRI imaging, because it's a bit of a different animal. It actually makes, oops, sorry, I need to go back to my
Is Klaus out for the moment now? Can you hear me? Can somebody hear me?
Yeah, I can hear you, Anna. I think Klaus is reconnecting. So
yeah, because otherwise I will take his presentation.
Yeah.
Okay. I'm in the same building. I'll have a quick check.
Yeah, there was something with his presentation. I heard some strange noise all the time.
Yeah, I think it got stuck. He's coming back.
He is back now?
Hi, Klaus.
No.
Sorry. Yes, hello, I'm back. Sorry for that. Somebody killed my internet here. No.
Do you want me to have the presentation that I screen it and that you tell me which slide and then?
I don't know. It should be good again. So at least it appears on my side. Okay. So I'll try to go back. Yep. I think we were here.
Yeah, you're back on slide 14. Yeah.
Good. Sorry for that. There we go. All right. So I was going to talk about the MRI technique, which is obviously something that we are pretty familiar with, because it is definitely one of the non-invasive and not say, detrimental imaging techniques that are available to us nowadays. So this is a different beast because it is making heavy use of quantum mechanic effects, and I'm not going to go into details, but we are making use of the, say, proton spin. Every hydrogen atom, which is a proton, has a spin and has a magnetic moment, and within a magnetic field, that is the long tubes in the MRI scanners, these spins align nicely with the field that is given by the tube, or the huge tube, indeed. Now, with a bit of RF, and that RF has to follow particular rules, which means that that frequency of RF needs to be 42.57 megahertz per Tesla. The Tesla is the field strength of the magnet of that MRI scanner. We can excite those protons in a particular way, and what the scanner in the second place then actually does is it measures the relaxation of that excitement in first place back to normal, and via tricks that have to do with gradient magnetic fields, so you're only sensitive for that excitement, for that excitation in a particular sliver of the total length of the bore of that magnet. You can then start to compute these slices and get contrast over the XY axis through the patient and build up images that you probably already saw a number of times, which is wonderful. So this is particularly sensitive to any tissue that we have in us that have to do with hydrogen atoms, and others are less, say, effective to look at. But obviously, you can create very, very detailed and insightful images that give a lot of data and insight into the particular state. And you can tell that this person here was not too well after all. Moving away from the that more quantum mechanic stuff into direct RF use at the end of a catheter that you indeed push into the patient. Here you see an image of this treatment in the liver, into a liver cancer, a tumor. You follow that typically via ultrasound, so you can see how far you push the catheter in. At the end of the catheter, you extend an antenna, and in that, and you radiate RF so that you have a certain particular volume that in that particular volume overheats and destroys that tumor, probably together with a bit of intact tissue, but that is then not so problematic. You will find the ablation technology used, for instance, in difficult to operate on liver tumors, but also lung tumors are treated like that. And the frequency here used is a couple of gigahertz typically. So basically just cook the tumor and destroy the cancer cells like that. Something similar is being done more or less regularly nowadays on heart arrhythmia treatments. So for folks that have a problem with the regular beating of the heart, typically in one of the volumes of the heart, people go around and produce little scars, and that scars prevent the, say, excitation of the heart to travel uncontrolled around the heart, which causes the arrhythmia. And you can have different positions inside the heart that you can treat with that technology. But it's basically the same idea as with this. You create a bit of tissue that you damage, and in that sense prevent excitations that run across the heart during a beat from taking unwanted paths, and that treatment is very effective. I actually had a number of friends that followed that one. A different type of treatment is the plasma treatments. And what you see here is an example. I hope you can hear it. Well, this is maybe a bit funny that we can play music based on this plasma torch, and that we can modulate this plasma in a way that it actually produces acoustic sound. The more relevant applications for these are, and where did I put them? I'm afraid, oh, no, sorry, are treatment of say, for instance, to activate particular surfaces, but also to sterilize in cavities, in teeth or tooth cavities. When the dentist has drilled holes into the tooth, you need to make sure that it is absolutely sterile before it's being filled. And then sometimes these plasma sources are being used because they create a relatively aggressive, also partly ozone plasma in here, and the oxygen in the ozone kills bacteria very effectively. So these are used for that kind of purpose, and also skin rejuvenation and this kind of applications are there in the medical field. This video with the music is basically just meant to show you the kind of mastery and control of the RF signal that you can have in order to create that kind of applications. Now, one of my favorites is hypothermia, or thermotherapy, where you locally heat up patients. Actually, that's also where our name Pink RF comes from, because we were developing systems at that time out of NXP, together with Erasmus University, or Erasmus Medical Center in Rotterdam. And we were allowed in there, and we have seen the patients, and it was very, satisfying that you could see that you can help people by developing this kind of technology. And in there, we had this notion of the pink ribbon theme, which is the breast cancer treatment. And we thought that the number or the color pink should definitely come back in our company name to also make a statement with respect to the applications that we would want to build and support. So the hypothermia in general is more or less localized irradiation of limbs or something like that with RF for treatment of cancer. And that can be one channel like here, but it can also be multiple channels when you want to treat deep tumors. And that is also what Erasmus currently investigates. And there can be up to 12 channels. So in our current case, it's actually 20 with, for instance, 434 megahertz. And you need to have very high degree of power control and phase control. As you can imagine, you're working on patients. So this must really be correct in order to deliver the energy where you need it. And so you need to have a closed loop control of RF. And you need to know about the phase of the signal, because you make use of superimposed waves inside the patient. And I have a video here from Sensius that should run now. It does, where you can see that from a number, this is, say, the part that you would want to irradiate and heat foremost. It is deep inside the body. So you take a number of sources from the outside and you create a field at the point where you actually want to heat most, which is superimposed all the sources, and you have a maximum energy delivery right there without, sorry for the rest, without the overheating any other position at the neck of the patient. As you can imagine, it takes a lot of modeling to predict all the superimposed wavefronts and the action on it in a patient, which has much more structure, obviously. This is how such a signal looks like. This generator here holds 4 channels so that you can stack these generators to make them all coherent, to work in a way that you can tune the phases between the channels so that you can steer those waves as we've seen in the other video a second ago. And the applicator in this case is basically water bags, which are called boluses, that make contact with the patient's skin. And inside the bolus, you have an antenna structure that radiates that power out. You can see here, for instance, the antenna connections that lead to inside the water bolus and then radiate the power into the patient, in this case, head and neck of the patient. Another example is something completely different. We have, for instance, these plastic tubes that are used for diagnostics and or other chemical reagents that need to be heated up. They only have 0.5 milliliter of liquid content typically, and we do that just 0.5 milliliter. You need to imagine that. And we use a 20-watt generator, for example, to heat it up in a particular cavity. So this is an applicator. We are putting the RF in on one side of this elliptical cavity and make sure on one focus point of the cavity, and the system is dimensioned in a way that the energy radiated here in the one focus point again focuses in the other point, which holds the tube, and we can heat the tube in that way in a very controlled way. A lot of simulations go into it, and I'm just showing you this to see that this is sort of a cross-section of the cavity. This is the antenna input. This is where the power then is being created close to the tube that you put into there. And it is a resonating structure, and for the experts amongst us, this tells you that there's a very shallow frequency, a very narrow frequency band, where actually the energy is being put into this unit. If you put a frequency into the system which is off with respect to that one where you need to be, you basically reflect all the power out. And this can also be used for process control. So if you do things well, you can heat this kind of small volumes very quickly, in a very controlled way. And this is how this looks in the end. And this is used for diagnostics, as I said, purposes. Another example, which looks completely different, is to heat up intravenous liquids like 0.9% isotonic saline solution for perfusion treatment. And then we have chosen in the end to build an applicator like that, which is running of 27 megahertz. It has capacitively coupled field into the volume where the liquid is flowing, actually. So there's no contact of any metal with the liquid. So this is a very clean applicator, and yet the power is being transferred into the liquid, and we can heat efficiently up to the necessary temperatures. And again, it takes a lot of simulations and engineering to end up with this kind of nice applicator together with the beaker structure to go into the field and help people. Now, that was it as far as I'm concerned with respect to the examples that I wanted to give you. My conclusion here is that, first of all, the RF and microwave assisted applications in the medical field are not new. They are definitely there, maybe less recognized, but they definitely exist. And that with the perfect controllability and selectivity of the radiation, that there still are many possibilities for novel applications to be developed. If you think about very, very clean heating of stuff, of matter, then the RF or microwaves are definitely a candidate to achieve that. And you don't need any surface that could be contaminated or any other liquid that could be contaminated in contact with the thing that you actually want to heat up in order to achieve the temperatures for your processes. I hope I could give you a bit of insight of how this works and what we see possible in the medical field and what is being used. And other than that, I'm open for any question. Thank you very much.
Yeah, thank you, Klaus. I take it over here, and very insightful. Thank you again. We have a few minutes because there was a small hiccup. Someone put on the magnetron while you were, and your Wi-Fi was probably. So I will give 5 minutes or so for questions. The recording will stay on anyhow. So for people that have an obligation at 4:30, feel free to switch off. But the recording will go on. So are there any questions to Klaus? You can raise your hand or. That was my watch. I have a question, Klaus. If I would, it's not a medical application, but if I would heat up my water in my kitchen with this technology, would that be more efficient than my current heater at the ceiling of my house? Could that be?
Sorry, you lost me there. With the heater of the ceiling, I'm
no.
lost.
So heating my water I use daily in the kitchen. Yeah.
Yeah.
With an instrument around it instead of a boiler or a CV installation at my ceiling.
Yeah, well, if you look at the water cooker in the kitchen, that is unbeatably effective because it is using all the energy to be put into the water. There's nothing more efficient than the water cooker in the kitchen, unless you use a different, like if you go to gas heating directly or something like that. No, so that would not give you any benefit. If you had, if you're concerned about the CO2 footprint and you could live off green electricity, of course, then it would matter. Then the technology allows you to heat whatever you want without going through fossil fuels being burnt. And to that extent, we are working on a number of other applications, and those all have to do with, the energy transition and upgrading CO2 or trying to produce hydrogen. And in that sense, my belief is that if it is about electrification of heating processes, there is this RF/microwave technology is the technology to be used.
Okay, thank you. Yep. Any other questions to Klaus? If not, feel free to Google on pink RF on what they could mean for you if you are interested to cooperate. Klaus, thank you again. I would also like to thank Tom and Anne from Hightech NL to help assisting in setting up the seminar. And from an electronic roadmap perspective, we keep you, and Hightech NL perspective, we keep you posted on a series of seminars we are addressing for printed electronics. Good also, if you can print, they should be flexible. So printed flexible electronics, we are working on that topic. So in the second half of the year, we will show some evidence and invitations on these topics. So thank you again for the call, and yeah, see you next time.
Thank you.
Okay. Thank you, Klaus. Thank you, Hans.
Hey, thank you. Bye-bye.
Bye-bye.